Hi, I'm Kelly, and this is Physics 2 Lab 3 Magnetic Field of a Bar Magnet. So as an overview, I'll be going over the introduction for this experiment, some procedures, data and observations, calculations, my code and GlowScript model, and finally some discussion questions to conclude. So as some background, the goal of the experiment was to characterize the magnetic field of a bar magnet at different distances on and off axis. I measured the magnet at different distances while accounting for the magnetic field of the Earth done through a magnetometer app. I then eventually created a linear model that was used when plotting the data. And so it's important to remember that the magnitude of the magnetic field due to a bar magnet falls off with distance. And this distance dependence can actually be expressed by an equation shown here, B bar. K equals the magnetic moment times the magnetic constant. I'll also be using the Biot-Savart law for a dipole with a magnetic moment to determine the magnetic field in my computational model. For my results, I found my mu to be 5.12 amp-meters squared. So for the procedure itself, I first downloaded the Teslometer app on my phone. Then I determined the direction of magnetic north by rotating my phone on my desk until the x component of the magnetometer equaled 0. Then I oriented a long piece of tape with marked increments in centimeters, oriented east to west. After this, I located the magnetometer by sliding my phone perpendicular to the tape in the x and the y direction, noting that the z component should not change. Finally, I moved my phone on axis and also took measurements of the magnetic field at a distance 45 degrees off the axis of the magnet, shown in the figure in the bottom right corner. For my on-axis data, I took the averages of my distance and magnetic field measurements and used the natural log to linearize them and give them a best fit line that's used to determine n and mu. For my off-axis data, I positioned my phone at distance d perp in the x and the y direction. The average was found to be 0.18 meters, and this was later compared to my computational model. I also made two observations in this experiment. I first found that the magnetometer reads 0 far away from the magnet. And second, that the x component of the magnetic field increases when the magnetometer approaches the magnet. For my calculations, I found the line of best fit from the Excel sheet and found that n equaled negative 3.18. I then found the natural log of k to be negative 14.471. By taking the exponential of the value gives k, and setting it equal to the magnetic moment times the magnetic constant gives the mu of 5.19 amp-meters squared. For my code, I defined the magnet and the moment for my experimental calculations. I defined a function to calculate the magnetic field using the field of the magnetic dipole moment shown in the code in the bottom left. The results of the code are shown in the GlowScript model on the right. I then rotated this model so that it's better to visualize the on-axis and perpendicular locations. I defined observations surrounding the magnet and used them to create our vectors. I then called a function to determine magnetic field at the location and made arrows showing the magnetic field at those observation locations. Finally, I used dperp to determine the magnetic field at an off-axis location, as shown by the magenta arrow that's circled. So to conclude, let's go over some discussion questions. So without orienting the experiment to compensate for magnetic north, the magnetometer readings would be skewed in the direction of magnetic north. Also, the difference between the computational and experimental values would be greater, because I would also have to account for the y component in my linearization and calculations. And second, if I were to stick the identical magnets together, I would likely get readings close to double what I measured in this experiment due to the principle of superposition. Thank you for listening.